Vector calculator?
So, I thought we'd look at a few more examples of tricky or just involved physics problems involving energy and work. So the first one we're going to do is number 8 in our textbook, which is this. So we have a 330 kilogram piano. It slides down a distance of 3.6 meters, and we know the angle of the ramp is 28 degrees. It's kept from accelerating by a man who pushes on it parallel to the incline, so it's kind of like he's letting it down slow. But I don't know if he's got some kind of mats down or something and he's moving the piano like downstairs. Something fairly practical that someone might have to do. So it's sliding down with him, but he's pushing against it to keep it from like sliding too fast and going and exploding at the bottom of the stairs. Right? So we want to calculate a variety of things. The force exerted by the man, that should be something back from when we looked at chapter 4 problems on forces, and I know we still need more practice with that on a ramp, so that's why I chose this one. And then we're going to calculate the work done by the man on the piano, and the work done by the friction force, and the work done by gravity, and so then we'll put them all together to come up with the net work being done in the situation. If these flies will leave me alone, which seems unlikely. So, first we need to figure out the work being done. So we've got a nice free body diagram that my assistant has put on the board for me. Thank you, Kosh. And we've got a coordinate system that we've chosen. So this time down the ramp is x. Why do you think they chose down the ramp as positive here?
Okay, that's the way it's headed.
Yeah.
Because that's the way it's headed. So that does make sense as a coordinate system choice. Of course, we always want to pick straight up from the ramp in like a normal force orientation as the y coordinate. Okay, so the free body diagram's got these different things. We don't want to draw a piano here, but this is our piano, this box. I think that was a good choice to simplify it, or just use a point. And we've got a guy that's pushing upwards. We don't show the guy just so we don't have extra stuff in our diagram, but he's pushing up. Let's also remember that where is the motion happening here? It's not drawn on there. It's actually still sliding down, and it told us the distances and so forth so we could compute the work eventually. But first we're just going to focus on the force, just like we did back in the day. So again, you can rotate this to kind of match and so forth. I'm just going to do the way that the book does it, and I think is kind of nice, the way that matches up with the memorized way today, by just looking at the geometry of the situation carefully. So here's that 28 degrees for theta that we've got going on. All right. So I'm going to apply Newton's law in both directions. So I'll start with the y component, and then I'll move on to the x component, and I'll apply F equals ma. Right? Very simple. So I'm going to say, looking at the y components, what do we have going on here? So remember, this is y going up this direction, so I've got the normal force. Very simple. But then if this is the y direction, what other vector do I have? It's not this or this, obviously. It's some part or piece of this gravity. It's the gravity that's being directed directly into the surface, or the ramp in this case, right? So you can see that that in this case is this right there. Are we clear on that? So if this is truly theta, which we'll talk about in a second, then what part of theta is that? Is it the sine of theta or the cosine of theta that this piece is? It's adjacent, right? That's adjacent to this theta, so it's going to be cosine. Which is weird, right? Because y is usually sine when we work with trigonometry, but you can see clearly from this picture why it changes to the opposite, I think. So this is going to be minus, because that's going down, that's going up, minus the magnitude mg times the cosine of theta. And since it's not moving, are we going to have may here? 0. I think I'm just going to assume at the beginning it's not moving to figure this out. Yeah, it's not moving up, that's for sure. That's true. Now, over here, are we going to be able to make that same assumption?
No.
I'm not sure. I don't think so.
Accelerating.
Oh, they said it's not accelerating. That's true, didn't we? They say that the man's just keeping it back enough. It's moving, but it's not accelerating. That's a key to the problem as well. So these will both be 0 actually in this case. Thanks for helping me out already. Very nice. So we've got that guy all done. So the only question was, why is this theta the same as the ramp angle of 28 degrees that they gave us to begin with? That's just geometry. Don't make this hard, okay? Like, and you don't have to remember this argument totally, but can't I like draw this little right triangle right there? This is theta, this is 90. What would this angle be right here?
90 minus theta.
That's 90 minus theta. But what is this overall angle right here? 90. So if that's 90 minus theta, and the overall is 90, then what's this?
Theta.
If you're not sure, 90 minus theta plus what equals 90 degrees? There it is in black and white terms. It's theta. So that's a proof that this dude is actually theta, okay? So I hope that that removed any confusion that you have about this whole ramp issue, flipping the sine to the cosine and vice versa. So let's continue, let's plug in here. So in the x direction, we've got a few different things. We've got friction going that way. Is that negative or positive from my setup?
Negative.
It's negative, so I've got negative force of friction. Is this negative or positive from my setup?
Negative.
I've got negative force of dude holding back piano. And is there anything else going on in that direction?
Force of gravity in the next one.
I've got the force of gravity. Sneakily, I've got this gravity component. Now, which way is that going?
Positive.
It's going the other direction, right? It's like this thing. It's like this right here. So that, based on this being theta, is the opposite or the adjacent?
Opposite.
It's the opposite. So opposite would be
Sine.
sine. So there's the reason that works like that. So since it's positive, I'm going to put it at the beginning here to make it make more sense. And it's gravity's magnitude times the sine of theta. There you go. I hope this makes everything crystal clear. Okay? So then because of what Gabe said, the guy's holding it back just enough to avoid acceleration, we can set it equal to 0. And now we can combine these to figure out, what did part A ask? Help me out, remind me.
The work done by the man on the piano.
I think part A said,
Force exerted.
so this force push is what we're looking for, right? So how do I put these together? You guys remind me? What goes with what? Because there's like 1, 2, 3 different things right now.
Force of friction is equal to
Force of friction is equal to the normal force
Or the coefficient.
times the coefficient of friction, which I think we're moving, so it's kinetic friction. And I think they told us the coefficient was 0.4, didn't
Yep.
they? So they gave us that this was 0.4, and there you go. So this is going to be from up here, we have the force of friction is mg cosine of theta, and we know that the coefficient between these surfaces is 0.4 because they told us so. So then I can take this and substitute it in for the force of friction, and I have everything here except for the thing I need. So I'm going to have F sub P, if I move it to this side, is equal to mg. So can you guys help me plug in the numbers and calculate it for me real quick? So what was the mass of the piano?
330 kilograms.
330 kilograms times gravity times the sine of 28 degrees was the angle of theta. And then, remember, I'm just adding this over here, so then I have minus the force of friction right here, minus 0.4 mg cosine of 28 degrees. So what is that? Someone calculate this for me quickly. Max is on it, I like it.
376.
What'd you get, Max?
224.67.
Do I have confirmation?
I differed a little bit.
I can check.
We got 376.
376, that's what they say. So sig fix, what we got for sig fix? 2?
Yeah.
We have 2.
380.
So 380. I just want to get this number correct. So 380 what? Units?
Newtons.
Newtons. So that's the force the guy is holding the piano back in order to achieve no acceleration or something like that, right? Okay, so the second part of the question says the work done by the man on the piano. So let's think about what direction that's going. So this is going that way. The piano's motion is trying to go which way? Down. So is it going to be a negative or a positive work?
Depends where you make positive.
Negative.
It's negative. You can prove that by saying, like we said earlier, theta, for the cosine of theta in the formula, work equals force times distance, only the parallel component. If we don't have to on this one, but if we wanted to put cosine of theta here, what is theta technically? It's 180, and the cosine of 180 degrees is -1. So that's why you're going to get a negative work, and you don't really need this on this problem. okay? Because they're both totally the same. The guy's pushing along the axis of motion. It's just anti-parallel. So that's what gives you the negative, okay? So you could say cosine of 180 degrees if you want, and then that'll give you -1. So the amount of force we know is that, and the distance moved, they told us, was
3.6 meters.
3.6. It's in meters. Good to go. So what do we get for the work the guy exerts on the piano?
Negative 1,368.
1,368
So sig fig.
units.
Joules.
Joules. And if we want to do sig figs, then I think we've got 2, so
1,400.
1,400 is the sig fig answer, but it's got to be negative because of the anti-parallelness
Yeah,
here.
because the units.
Okay? So part C of this problem says what?
Work done by friction.
The work, oh, and I just erased friction up here, dang it. So the force of friction, what did we have, was 0.4 mg, and was it cosine or sine? Cosine of theta. I think we might have to use that cosine here, yeah? So, so we want the work done by friction, that's all they said, right? So again, let's think, is this gonna be a positive or a negative work?
Negative.
Why?
Let's look backwards.
Friction is going against the motion, just like the guy's push, so it's also going to be negative. Its angle would also be technically 180 degrees, or anti-parallel, which will give you that -1, okay? So this time, though, we have to be a little bit careful. Remember, the frictional force already had a cosine built into it, so that's a little bit sneaky. So we're going to have to say, okay, so this was the work, I should label it, right? I'm going to say work guy, I'll just call it work guy, that makes sense to me. So this one's going to be work friction. So the work due to friction is going to be that same 3.6 meters times the force of friction, which is going to be 0.4 mg cosine of 28 degrees. Why do I have to have this cosine of 28 degrees? I thought the angle was 180 degrees.
It's
It's
part of
the
the friction.
Go back to your diagram up here and look at the friction. And that friction was calculated, I guess I erased it, I shouldn't have, but a second ago we had that the friction was based on the normal force times cosine of theta, and the normal force, if you remember, was calculated by using the ramp issue, which already had a cosine in it. So I think that's kind of sneaky. So what does this come out as?
I got negative 4,111.
4,000.
111.
Can I get confirmation from someone else? Same, Jamie? Okay, we'll count it then. So what's the work? What's the unit again for work?
Joules.
Joules, just like energy, right? And with sig figs, then we'd say like something like that, right? Okay, so the final question. Are we on the final question yet? Is there one?
No, we got work done by gravity.
Work done by gravity. So of course gravity is also doing some work, but only this purple component, right? Only this purple component of gravity is doing some work. So was that the sine or the cosine? Look at your theta. Remember the theta is right in this corner right here. So again, that's going to be the sine this time, right? Or you could just go back and find where you used it earlier, but that's fine. I like to go back to the picture and make sure I know what I'm talking about. So the work done by gravity is also going to occur across this movement of 3.6 meters as it slides, and it's going to be, gravity was mg sine of 28 degrees, and so that's what we need there. Of course, m and g staying the same as they have for the rest of the problem. So can you guys tell me what that is?
5,466.
Confirmation?
Yep.
Yep. Okay. So technically when we do work, I thought the work formula had a cosine in it, right? Don't be just thinking about formulas without thinking about why the parts of the formulas are there. That's what bad physics students do, you know what I mean? You've got to be realizing why. Technically, do I have a cosine here? Here's the force, here's the distance, and this would technically make sure I only get the parallel part. What angle would I put in here? Think about it. Remember, we're thinking gravity, which is that purple little piece up there. this is going this way, and the motion was also going down the ramp. So the angle between them, just like that situation Daniel had earlier, is going to be 0, and the cosine of 0 is 1. So did I really need to have this? Well, yes and no. It depends on how comfortable you are with where things are moving. The key is that when you're doing work problems, you think about the angle between the motion and the force, which could be anything. Okay? Make sense? So I could have just left this off and I'd have been fine, but just by luck, right? So this is positive now, joules. So what do we get for the net work? Well, we just add them all up and see what happens. What's happening work-wise total or net? Well, we've got this much work that gravity is doing, which it kind of makes sense that this is bigger than some of those other numbers because this is a big piano, and the whole point is that like guys having trouble with piano because it's heavy, and the reason it's heavy is because that's the weight of the piano, which is due to the force of gravity. If you're on the moon or in a swimming pool, that weight changes very differently, and we'll do stuff. We've already done some problems on the moon. We will do stuff with buoyant forces in a swimming pool and understand exactly why that works as well. So this is the biggest number, even if you didn't guess it, even if you're like, for my diagram it looks teeny, these look big. Well, that's because I didn't draw stuff to scale, right? Gravity is what matters the most here. Let's see if it gives us a positive work. I don't know. Depends how hard guy is pushing.
You should make that work sig figs too if you're going.
I should, thank you. That's a very good point. So what should it be then?
5,500.
Thank you, Emma. So what do we get then?
0.
That's 41 and 51 and 55. Does it come out to 0?
Yeah.
So, does this make sense?
Yeah, because it's not accelerating.
Because it's not accelerating, yes it does. It does make sense. So, there you go. I hope that at least this problem, while conveying some concepts about work, really helped clarify the issue of the ramp and why it's opposite. I think we got it, but I don't know. I'm not you guys. So one more example I wanted to look at was one that involves a combination of different types of energies that we've seen so far. And I think we've really seen 3. We've seen the expression, the equation for kinetic energy, or 1/2 mv squared. We've seen the expression for things that involve gravity, like our dropping ball that we have here. It's going to fall. That'll be potential energy due to the height of the ball above some defined coordinate origin. And that's mgy, of course. And then we also have spring potential energy, which we've learned is 1/2 k times the displacement, or the ability of the string to stretch, squared, kx squared usually. Okay, so in this situation, we're going to have a ball fall onto a spring platform, and then that spring is going to compress itself 15 centimeters. We also, of course, know how far that the ball falls. And what we want to do is use just the fact that we know the mass of the ball and these 2 displacements of the spring and the fall of the ball to figure out how strong the spring is. In other words, the spring constant K. So that's the goal here, is to figure out the spring constant K. So that's not a whole lot of information, so it's pretty interesting, I think, that you can actually do this just using conservation of energy. So this will be a closed system. We'll just ignore the effects of friction or the heat due to heat, sound, any other kind of small energy leakage that might occur. So we'll get a pretty accurate answer because I don't think that there's going to be too much energy leaking outside of the system through dissipative or dissipated forces. So energy is pretty much conserved, and we've just got to think about our system being from the beginning, when the ball is dropped, to the end, when the ball compresses the spring. So at the beginning, we're going to have some gravitational potential energy, possibly some spring potential energy, and maybe some kinetic energy as well. So we'll combine all of those into one statement. So kinetic energy is going to be 1/2 m, I'm going to call it V1 for that point in time, squared, plus the potential energy, mg, and this is up above, so I'm going to call it y1, plus spring energy, 1/2 k, and usually you say x here, but we're kind of going up and down with these springs, as you can see over there, so I'm going to call it ky1 squared. So that's the beginning point when we're up here. The end point is going to be down here once the ball compresses the spring, and I kind of drew it separately, but of course it's just compressing that spring right there. So one thing I need to do is choose where my y coordinate system, xy coordinate system is going to be. So I think I'm just going to make this choice, and you could make multiple different choices. I'm going to call my coordinate system 0 or 0 height right there. Okay? So that's the beginning. Now once it's down here, we're going to have possibly still some kinetic energy. We'll have to think about that. Possibly still some gravitational potential energy. We'll have to think about that. Now we've got height too. Mass, of course, is the same. And possibly still some kinetic energy from, or excuse me, potential energy from a spring. So now we just need to think about which quantities potentially go to 0. So thinking about our system from point 1 to point 2, from when the ball is up to when it compresses the spring. So let's see, is the velocity at the beginning going to be 0? I think so, because that's right before we drop it. So this whole term is going to go to 0 because of the velocity. MGH or Y1, I think that the Y coordinate here is going to be above, up there. The ball is actually that high, so it's going to be 55 centimeters that goes in there, or excuse me, goes in there. So that's not going to be 0, I don't think. We've got a mass and a gravity. 1/2 K, that's the strength of the spring. Let's think about Y1. So what does this Y1 refer to? You know, I don't think that these are necessarily the same, so maybe I shouldn't have named them the same in the first place. That led to some confusion, and I had to edit the video a second ago because I was focusing too much on my explanation and not enough on my labeling. So instead of calling this Y1, or instead of calling this Y1, I could make a different choice. So you know what, this is like the height of the ball, so I'm going to call that H1 and leave this one as Y1. So then over here, what I'll have to do is keep this one as H2 and Y2, like I already kind of did a second ago. So I need to be consistent with my labeling. Okay? Alright, so we agreed that the height is going to be 55 centimeters, but Y1 is kind of having to do more with the spring than the ball at this point. It's the amount that the spring has been compressed, and at this point the spring hasn't been compressed, it's right there at 0. So you can see that this term is also going to go to 0 because of the spring not being compressed at all. When we land over here, I think the velocity is going to go to 0 again. We're not going to have any kinetic energy for that reason. The height of the ball will now be down below here at 15 centimeters. And what about the level of the spring at that point? So the spring will also have been compressed to that 15 centimeters. So these will both be 15 at that point because the ball and the spring will be in the same location. So, okay, again, we were trying to solve for K, so let's see if we can plug in some numbers and figure it out. So we've got the mass of the ball, we've got gravity, we've got the height. I need that in SI units. Centimeters won't cut it, so I'm going to have to go 0.55 meters, do a little unit conversion. And then over here I have, nope, I don't have a half there. I have the mass of the ball, I have gravity, I have the height at this point, which is going to be negative 15 centimeters, so negative 0.15. And then I have plus 1/2, the thing I want, K. I don't see any other variables so far, so we should easily succeed in solving for K. And again, I have negative 0.15 centimeters. This time it's squared there. So I can go ahead and solve and say, well, K, let's just throw stuff this way, I guess. We'll throw that number this way. It's negative, so I'm going to add it. And it's almost the same, but this is different than this. So you know what? I'm just going to do some factoring at the same time just to make this nice and more expressible, more easy to see, I think. So I'm going to factor that out of the 0.55, and then remember we're going to add this quantity to the other side, and so we'll factor that out and say plus 0.15. That makes our calculator part a little bit easier. So now I've got that, and then I just need to compensate for this, so I'll multiply by 2 to get rid of the 1/2. So I'll put an extra 2 right there, and then I need to divide by my negative 0.15 squared, and you can see the negative's not going to matter in that part, but it did matter because of this aspect of the calculation. So let's see what we get. All right, so I'm just going to get a fraction going by using alpha y equals, go 2 times 2.6 times 9.8 times the quantity 0.55 plus 0.15, which is really just 0.7, but whatever. And I've got 0.15 squared here. That negative is going to, of course, be turned to positive. So I get 1585, and I just need to think about sig figs. So maybe this spring is pretty solid. I mean, it's experiencing a ball that drops on it of 2.6 kilograms. So it's probably a fairly strong spring. I think that's a pretty strong spring. So sig fig wise, I think we had 2 sig figs here, here, and here. So I'm going to go with 2 and go 1600. So the question is, once we have our spring constant K, it's 1600 what? We need to include the units here. There's a variety of ways you could do that. You could go back up and look at one of these equations that you've already used and try to do it that way. So let's go with that approach first. So potential energy involves the spring constant, and that's half K times like X or Y squared. We used Y, I'm just going to call it X. So really, any numbers in the equation, any constants don't matter in terms of the unit analysis, so I can kind of get rid of this. Then I can think about the units for each quantity. So energy, of course, is measured in joules. K is what we're trying to figure out, and X, the SI unit, is of course meters, and here it's being squared. So you can see that one expression for the spring constant would be joules per meters squared. Since the meters are squared there, I need to either go back and break down joules, which is one option. And if you're watching the video, I'd really encourage you to go back, try to figure out a way to break down joules into more elementary units and simplify, maybe cancel out at least one of those meters. Another way is to just pick a simpler formula. So potential energy was one equation that had the spring constant K in it. A simpler one is, of course, just the force due to a spring that Hooke came up with. In other words, Hooke's law, which is F equals negative kx. This is a little bit simpler formula. Force, of course, is measured in newtons. K is what we're searching for again. -1 is a constant, so I don't need that. And X again is in meters. So here you can see that K is measured in newtons divided by meters. And that's usually the accepted version of the units for the spring constant. Of course, you could use F equals ma or something like that to break down what the force unit of newtons is, and break it down even more simply. That's the accepted traditional way to express a spring constant in units. So like I said, it'd be good for you to just experiment with this and make sure that it's actually the same as that, using some other elementary unit analysis. I hope that helped you apply conservation of energy. I'll see you next time.